And you know, whenever you are going to measure SFDR, I'm not going to give one input signal. I'm going to give two tone. That's why I said two tone. Tone means one frequency. The tone corresponds to one frequency. So two tone means I'm going to give linear combination of two frequencies which are very close to each other. So omega 1 A into cos omega 1 t plus cos omega 2 t. And for all our analysis, we consider sinusoidal or cosine signal because you know the signal very well. And from cos you can get sine, from sine you can get cos. All the trigonometric formulas are available. That's why instead of taking any unknown signal, wherever possible we work with sine and cos. Okay, so for SFDR, for measuring SFDR, we will always give a linear combination of two tone signal. I am assuming both the signals are having the same amplitude, capital A. And omega 1 and omega 2 are very close to each other. So as you see in the SFDR diagram, this is for a dynamic range, you see only one peak we have. So this is our actual signal. This is our noise. But SFDR, you see, you have two peaks which are equal. So these two peaks correspond to two tones. One is F1, one is F2. Since the amplitudes are going to be same, the power is also going to be same. So remember, for SFDR, always we take two-tone signal and substitute this V in the equation for current. And if you substitute and simplify, we have done this already in the last class. When what happens if you put V square, what happens if we put V cube, we have seen. So we can write all the trigonometry cos square in terms of cos cube in terms of cos. So we have simplified all these things. So after substituting and simplifying, the first two terms alone is written here. The DC component and fundamental component are given. So DC, see, this term does not have any frequency, so it is a DC term. See, our signal was not having any DC component. Now see, a DC component is getting added. So DC component it is nothing but it will shift your signal upwards or downwards. Nothing, it will not do modification. It will not do any modification to your signal. It will just shift your signal upwards or downwards. You call it by the name clamping. So it will clamp the signal on the positive side or on the negative side. Okay. This is my DC term and this is my fundamental component. See, this is our frequency of interest, right? So this amplitude you see, it is C1 into A plus 9 by 4 C3 into A cube. So we can see the amplitude is A, what the input amplitude is A, but the output amplitude is A cube. So the amplitude is getting boosted up. So this is a good sign for us because our required frequency of interest is going to have a larger amplitude than the one what is separate. So the amplification is happening here in the low noise amplifier. So this is the first two terms whatever we got. Now we have the remaining terms also. If we expand, you see here, this is our second harmonic term. This is the third